This is a system called quadrature phase shift keying. It's similar to the phase shift keyed signal we just looked at and modulation we just looked at, but it takes it one step further in that we have a carrier signal with a phase angle of 0. This is a straight up carrier signal. And then we have a 90-degree phase shift applied to that carrier, so it produces a quadrature carrier. This is going to be cosine 2 pi FCT minus 90 degrees into a second mixer. So we start with a random binary stream 00011011, and now we want to break this into 2-bit words with a serial in parallel out shift register. So we're going to clock in the bits into the shift register, take the least significant bit to the upper path, take the more significant bit to the lower path. So we clock in 1 1. This least significant 1 goes to the upper path. This next one goes to the lower path. Then the 0 goes to the top path, and the 1 goes to the bottom path. And then let's see, we've got a 1 to the top path and a 0 to the bottom, and then a 0 to the top and a 0 to the bottom. You'll notice this is all of the possible 2-bit combinations, 0001 1011. And this binary stream is then the input to a comparator, and the comparator maps this is the input voltage, either 0 volt or 1 volt, corresponding to logical 0, logical 1. A logical 0 maps to minus 1 volt, and a logical 1 maps to plus 1 volts. So this is essentially the same. This is produces a polar non-return to 0 signal. So we have polar non-return to 0 as this signal labeled I of t for in phase, and also for this signal labeled Q of t for the quadrature signal. So the in phase binary polar non-return to 0 signal is mixed with the straight up carrier, and then that is applied to the summing amplifier. And then the quadrature signal is mixed with this phase quadrature carrier, the one that's been shifted 90 degrees, and then it is added in the summing amplifier, and it produces a quadrature phase shift keyed signal. So we want to first write the output signals for the output of this block diagram, and there's going to be 4 different equations depending upon the inputs, the binary inputs, and here are the 4 possible binary inputs: 0001 1011. So we start with 00. So we have a logical 0 into the top comparator that maps to a minus 1, and a logical 0 in the bottom comparator maps to a minus 1. Through the top branch of this, the in phase signal will be minus 1 times a cosine 2 pi FCT, and then that's going to be added with the quadrature signal. So minus 1 times cosine 2 pi FCT, let me write this as a phi phi quadrature phase shift keying of t. And the first signal, we have a minus 1 times a cosine. Let me put the minus 1, incorporate that as a 180 degree phase shift. So this would be cosine 2 pi FCT minus 180 degrees. Okay, so that's the signal. That's the signal that comes out of this top mixer. Then we're going to add to that the signal that comes out of the bottom mixer, which is going to be, so we have a logical 0. This is the more significant bit. Logical 0 in, that'll be a minus 1 as the Q signal. Minus 1 times cosine 2 pi FCT minus 90 degrees. Let me incorporate that minus sign as an additional 180 degree phase shift. So then we would add plus cosine 2 pi FCT, and then minus 90 minus an additional 180 degrees is going to be minus 270 degrees. Okay, so this is the quadrature phase shift keyed signal for the input 0, 0. If we have the input 0, 1, so the quadrature phase shift keyed signal is going to be 1 is the least significant bit, that's the in phase. 1 maps to a plus 1, so we have 1 times cosine 2 pi FCT, so that's simply cosine 2 pi FCT, minus a phase angle of 0, because we don't have any phase shift, because I is a plus 1, because the least significant bit is a 1. More significant bit is a 0, so that maps to minus 1. So we have minus 1 times cosine 2 pi FCT minus 90. Again, let's put the minus sign, incorporate an additional 180 degree phase shift. So this would be plus cosine 2 pi FCT minus 270. Then for 1, 0, let's see, we're taking the least significant bit now is 0, maps to a minus 1, so we have cosine 2 pi FCT minus 180 equals cosine 2 pi FCT minus 180. And then the more significant bit 1 maps to a plus 1, and that would be 1 times cosine 2 pi FCT minus 90, so plus cosine 2 pi FCT minus 90 degrees. And then finally a 1 and a 1. Least significant bit 1 maps to plus 1 for the in phase signal, so phi quadrature phase shift is equal to cosine 2 pi FCT minus 0 degrees, because we don't have we have a plus 1 times this cosine, and then we have a plus 1 times the second cosine, so plus cosine 2 pi FCT minus 90 degrees. Oh, there we go. Sorry. Get it on the screen. Okay, so these are the equations for the quadrature phase shift keyed signal depending upon the input. And the input in this case are 2-bit words. These are individual symbols. And instead of transmitting this signal 1 bit at a time, we're transmitting one symbol at a time. Now I want to draw the constellation diagram for this quadrature phase shift keyed signal. So I need to draw the point in the constellation diagram for each one of these signals, and the way we're going to do that is we'll draw and represent each one of these cosines as phasors, and then draw the corresponding point on the complex plane. So the constellation diagram has the imaginary axis vertically, the real axis horizontally, and we plot the points for each of the individual equations. Let's start with the point in the constellation for the symbol 0, 0. We have a cosine 2 pi FCT minus 180. The phasor for this cosine has an amplitude of 1 and an angle of minus 180. So with an angle of minus 180 and an amplitude of 1, 1, 2, 3, 4, it lies right there. If we were to draw it in as an arrow, as a phasor. And then the next signal has This the phasor for the second cosine has an amplitude of 1 and an angle of minus 270. The angle of minus 270 points all the way to there. This is minus 270 degrees. And if we were to draw the phasor with a length of 1, let me if I can get this straight here, right to there. Okay. Now the sum of these two cosines would be represented by the sum of their two phasors. So when we add these two phasors together, as we do, tail to point, then we get a point in quadrant number 2. 1, minus 1 along the real axis, and plus 1 along the imaginary axis, and this is for the symbol 0, 0. That's where it falls on the constellation diagram. Now we go to the next equation. 1 with an angle of 0. 1 with an angle of 0 falls about right there, I think. Yeah. This is 1 with an angle of 0 on the real axis. And then again, we're adding to that 1 with an angle of minus 270. That's this phasor. And when we add these two together, we get this point in the constellation diagram. And that point in the constellation diagram corresponds to the input 0, 1. So this is for 0, 1. For 1, 0, we have 1 with an angle of minus 180. That's 1 with an angle of minus 180. We've already got that one shown. And we add to that a phasor 1 with an angle of minus 90. So that's 1, 2, 3, 4, 5, 6. This is 1 with an angle of minus 90, and we add the two phasors together, and we get this point, which is for the signal 1, 0. And you won't be surprised to learn that the last one is 1 at an angle of oh, I drew the wrong one. Never mind. See, 1, 0 is 1 with an angle of minus 180. That's this one. Plus 1 with an angle of minus 90. That's that one. So this should be, that's not 1, 0. 1, 0 is right here. I knew I could hear you yelling. I could hear you all screaming. You got the wrong one. So this is 1, 0, and the final point in the constellation diagram, 1 with at an angle of 0 plus 1 at an angle of minus 90 corresponds to 1, 1. This is 1, 1. Okay. So these are the 4 points in the constellation diagram for this quadrature phase shift keyed signal. You can draw block diagrams for other signals that have 4 points in the constellation diagram that would fall in other places. Now it's a different question trying to decide which constellation diagram serves the purpose better. But this is the constellation diagram that results from this system block diagram. Now you'll notice these all fall on the if we draw these points, they're all equidistant from the I can't draw a circle, equal distance from the origin, so they all fall on this circle, and the circle has a radius of these are 1 and 1, so it's a square root of 1 plus 1 squared plus 1 squared, so the square root of 2, and they have angles of minus 45, minus 135, and plus 45 and plus 135. Okay, so that's the constellation diagram. You may recall the quadrature amplitude modulation from several weeks ago. It had a very similar block diagram for the modulation system, and as you might expect, we will have a similar block diagram for demodulation. We take the quadrature phase shift keyed signal into a mixer, mix it with a replica of the carrier. We also phase shift the carrier to produce a signal that's cosine 2 pi FCT minus 90 degrees, and mix that with the quadrature phase shift keyed signal. Both of these signals are then low pass filtered. We then apply an analog to digital converter, and then which will produce zeros and ones. The zeros and the ones are fed into a parallel to serial shift register, so we clock in parallel numbers and clock out the corresponding serial numbers, and in this way reproduce the bit stream that served as the input for the modulator. So we have to look at each one of the symbols as it goes through this demodulation. So we start with the symbol 0, 0, the quadrature phase shift keyed signal that we used for 0, 0, this is a T, is cosine minus 180 shift plus cosine minus 270 shift. So this is cosine 2 pi FCT minus 180 degrees plus cosine 2 pi FCT minus 270 degrees. Okay, so with this symbol we apply that this is the modulated signal applied to this top mixer. It is mixed with cosine 2 pi FCT, and then that's passed through a low pass filter. And then let me call this signal R1 of T right here, just to give it a name. And R1 of T is equal to, we're applying a low pass filter to the output of this mixer, and the output of the mixer is the quadrature phase shift keyed signal times the replica of the carrier, the cosine. So we have cosine 2 pi FCT minus 180 plus cosine 2 pi FCT minus 270. That's multiplied by cosine 2 pi FCT, and then we low pass filter. So now we distribute the cosine across these two terms. So in each case we have a cosine squared. So it's going to be we're applying a low pass filter to let's see, cosine times a cosine. I'll apply the trig identity. We have a 1/2 cosine of the difference of the angles. So 2 pi FCT minus 180 minus 2 pi FCT is just minus 180. And then for the second term, plus a 1/2 cosine the sum of the two angles. So that's going to be 2 pi times 2FC times T minus 180. So that's this cosine times the first cosine. We have the difference of the two angles, 1/2 the difference, cosine of the difference, plus 1/2 the cosine of the sum of the angles. And then we add, for the other cosine times cosine, 1/2 cosine the difference, 2 pi FCT minus 270 minus 2 pi FCT is just a minus 270 degrees, plus a 1/2 cosine, and then the sum of the two is 2 pi times 2 FCT minus 270 degrees. Okay, so we need to then low pass filter those four terms. So see, 1/2 cosine of minus 180 is minus 1. And 1/2 cosine of 270 is going to be 0. Okay, then the low-pass filter is going to filter out these high-frequency terms, both of these high-frequency terms, and we're left with minus 1. So signal R1 of t is going to be equal to minus 1, and the minus 1 corresponds to a logical 0. So you would set up the analog to digital converter, minus 1/2. There we go, minus 1 times 1/2. So we get minus 1 times 1/2. You could then devise an analog to digital converter that would map minus 1/2 as an input to an output of logical 0. So that's through the top path. If we go through the bottom path, we've got, let me label this R2 of t. R2 of t is equal to, again, the low-pass filtered version of, we have this signal cosine 2 pi fct minus 180 plus cosine 2 pi fct minus 270, and then we multiply that by cosine 2 pi fct minus 90 degrees. Okay, so again, we've got the result is a low-pass filtered. We've got a cosine times a cosine. Let me do the trig identity. That's going to be 1/2 the cosine of the difference of these two angles, 2 pi fct minus 180 minus 2 pi fct, and then we have minus and a plus, plus 90. So we have minus 180 plus 90 gives us minus 90 degrees. And then for the other term, plus a 1/2 cosine of the sum of these two angles. So that's going to be 2 pi times 2 fct. And then we add minus 180 minus 90. That's minus 270 degrees. That's the first multiplication. And the second multiplication, we have plus a 1/2 cosine of the difference of the angles, 2 pi fct minus 270 minus 2 pi fct, that cancels, then 270 minus a negative 90, so that's 270 plus 90 is going to be minus 180 degrees, plus a 1/2 cosine, and the sum of the two angles is going to be 2 pi times 2 fct. There's minus 270 minus minus an additional 90. That's minus 360, if I didn't lose track. So cosine of minus 90 degrees is 0. Cosine of minus 180 degrees is minus 1. The low-pass filter eliminates these two high-frequency terms. So what comes out of the low-pass filter is simply minus 1 times 1/2. So that's the signal that is applied to this analog to digital converter, and we can set that up so that maps again to a logical 0. So the first logical 0, that was that was the least significant bit. The second is the more significant bit, and they're both zeros anyway. So the output signal symbol is is 0, 0. Okay, so we've successfully demodulated. When the input is a 0, 0, we've demodulated an output that is also 0, 0. Okay, if we were to continue with this investigating this demodulation system, now we have to go to the other symbols. This was just for 0, 0. So for the next symbol is 0, 1, and the quadrature phase shift keyed signal is as we worked out before with the symbol 0, 1. First cosine has a phase shift of 0 plus a cosine with a phase shift of minus 270. So this is cosine 2 pi FCT minus a phase shift of 0 plus cosine 2 pi FCT minus a phase shift of 270 degrees. So now we have to work out the signal that comes out of the low-pass filter for in both of the in-phase demodulation and the quadrature phase demodulation, and that would make R1 of t equal to the low-pass filtered version of this signal, cosine 2 pi FCT minus 0 degrees plus cosine 2 pi FCT minus 270 degrees, and then that sum of cosines is multiplied by cosine 2 pi FCT and then low pass filtered, and you would do the same procedure. Distribute this cosine across this sum, so we have a cosine times a cosine, apply the trig identity, then we have a cosine times a cosine, apply the trig identity, apply the low pass filter, and determine what the output signal R1 is. I won't bother to do that. I went through this calculation with 0, 0 in sufficient detail that I think you can replicate this process, and you can find the output signal. And similarly, R2 of t is the low pass filtered version of, we have this same modulated signal, cosine 2 pi FCT minus 0 plus cosine 2 pi FCT minus 270, and now that is multiplied by the phase shifted carrier, the quadrature carrier, cosine 2 pi FCT minus 90. That's multiplied by cosine 2 pi FCT minus 90 degrees. And we take the low pass filter, and again same thing, distribute the cosine across. We have a cosine times a cosine, apply the trig identity, then a cosine times a cosine, you apply the trig identity, then apply the low pass filter, and you'll find the signal that comes out of the low pass filter in both cases. If it's a plus 1/2, that maps to a logical 1. If it's a minus 1/2, well, let me just show you. I'll do this one more, and that will be enough. Let's go with R1 of t, low pass filtered version of, I'm working on this top one. We have cosine times a cosine gives a 1/2 cosine of the difference of the angles, 2 pi FCT minus 0 minus 2 pi FCT is just cosine of 0 plus 1/2 the cosine of the sum of the angles. When you add them together, we get 2 pi times 2 FCT minus 0. That's and then for the second multiplication, plus 1/2 cosine the difference of the angles, 2 pi FCT minus 270 minus 2 pi FCT leaves minus 270 degrees, plus a 1/2 cosine. The sum of the angles is 2 pi times 2 FCT, and then minus 270. 270 minus 0. And this now is low pass filtered. Cosine 0 is 1. Cosine minus 270 is 0. Low pass filter filters out these high frequency terms, and we get R1 of t is equal to 1/2. 1 times 1/2. This maps to a logical 1. And then R2 of t is a low pass filtered version of, and we have cosine plus cosine times this cosine, so I'll apply the trig identity. Cosine times a cosine is 1/2 cosine of the difference, 2 pi FCT minus 2 pi FCT minus 90. That leaves a plus 90 degrees, plus a 1/2 cosine, and the sum is 2 pi times 2fc times t minus 90 degrees, then plus 1/2 for the second multiplication. Cosine, or the angles, the difference of the angles, 2 pi FCT minus 270 minus 2 pi FCT minus 90. We get the 2 pi FCTs cancel. Minus 270 plus 90 gives minus 180, plus a 1/2 cosine 2 pi times 2 FCT, and the angle is minus 360. Not that it matters, because let's see, cosine of 90 is 0 degrees, cosine of minus 180 is minus 1. Low pass filter takes out these high frequency terms, so we get R2 of t is equal to minus 1/2, and that maps to a logical 0. R1 is the least significant bit. R2 gives us the most significant bit. So the symbol is 0, 1. Okay, so we successfully demodulated that symbol as well. In the interest of time, I worked out the demodulation for the final two symbols, and you can follow along with my calculation, or it'll also be in the notes. This is for symbol 1, 0, and finally for symbol 1, 1. I have worked out the MATLAB numerical simulation for this quadrature phase shift keyed signal. The constellation diagram we've already drawn. This produces exactly the same kind of constellation diagram as we saw before for the 4 symbols 0, 0, 0, 1, 1, 0, and 1, 1. I've got message signal M1, which is a polar non-return to 0 signal, which is illustrated with the in-phase binary signal. Logical 1s are 1 volt, logical 0s are minus 1 volt, and that is applied to the mixer with the straight up carrier, and then to the summing amplifier. That's the second. The quadrature binary signal is also polar non-return to 0. So logical 1 is 1 volt, logical 0 is 0 volts. The way I have it here, it looks like the more significant bit is in phase, and the least significant bit is quadrature phase. So to tell the truth, that's the opposite of what we have of what we have in this diagram. So the constellation diagram will have the points in the same places. These symbols might be at different locations, but you can take the time to figure out exactly where the symbols fall if you wish. But I won't take the time to work out the constellation diagram. It would be the same process, and we would still have 4 points as we do on that other diagram. I'm more interested now in the numerical simulation. So we have an in-phase binary signal. This is a random string of ones and zeros. And the quadrature binary signal, which is a random string of ones and zeros, and they're divided into 2-bit symbols, and the 2-bit symbols proceed randomly as well. The in-phase carrier has a phase angle of 0, and the quadrature carrier has a phase angle of 90 degrees, which you may or may not be able to see from these traces, but this one does have a phase angle of 0, and this one does have a phase angle of 90 degrees. The in-phase carrier is mixed with the in-phase binary signal. Where did that go? Yeah, with the in-phase binary signal. The quadrature carrier is mixed with the quadrature binary signal, and the two signals are added together. And then the result is shown on the bottom of this page. This is quadrature phase shift keyed signal. It has a constant amplitude of the square root of 2 because we're adding together two cosines that are out of phase with each other, 90 degrees out of phase with each other always, and so the amplitude is constant apart from some numerical artifacts here and there, but it has phase shifts of either 0, plus 90, minus 90, or 180 degrees, and you can see where these phase shifts are occurring, and they correspond with the locations where the symbols change in our two input binary signals. The spectrum of the carrier signals, as you would expect, the magnitude looks exactly the same. Pair of delta functions at the carrier frequency. That's not very exciting to look at. The spectrum of the in-phase signal, I found this by using MATLAB, taking the Fourier transform to get this estimate of the spectrum. And again, it has this sinc squared shape, and it has a first null here at not the initial bit rate, but at the symbol rate. We're sending a certain number of 2-bit words per second, so we have a certain number of symbols per second. So this bandwidth is equal to the symbol rate. If we look at the spectrum of the quadrature message, it looks exactly the same as you would expect because they are both random binary streams. So it's got the same shape. Now the total signal, modulated signal, will have this spectrum shifted to the carrier frequencies, and this spectrum will also be shifted to the carrier frequencies with different phase angles. This is just plotting the magnitude, and then the two spectrums will be added together, and this is what we find. That's not surprising. These are sinc squared shapes that are added together, centered at the carrier frequency, plus and minus the carrier frequency, and the overall bandwidth is twice the symbol rate.